Hello, my name is Aiden Riley, and this is my lab report on Lab 3 circuits. The purpose, pretty simple, observe how batteries, capacitors, and resistors interact within a complete circuit, utilizing circuit analysis to predict the outcomes, and ultimately getting our experimental data using ammeters and voltmeters. The result of the experiment was, first, a change in voltage across a complete circuit will always sum to zero, and second, increasing resistance in an RC circuit increases charging and discharging time of a capacitor and vice versa. The fundamental principles to know: Kirchhoff's voltage and current laws, which can be summarized as the voltage across a loop will be equal to zero, and the current in and current out will be equal to each other. Additionally, we need to know some fundamentals of resistors and capacitors, particularly their two equations and how they work or summate in series and parallel. The first part of the experiment was measuring current. Modeling it, we simply used Ohm's law and resulted in a zero point zero 0.02 amps experimental outcome or modeled outcome for the circuit as a whole, just by using the information we knew about the circuit. And experimentally, we got 21.1 micro or milliamperes, which is approximately equal to the model. The second part of the experiment was pretty simple. Determine the effects of the voltmeter in series and in parallel. In series, the voltmeter will get a reading of the overall voltage of the entire circuit. However, it will interrupt the current as it has a very large resistance and make it so that ammeter readings are just zero. In parallel, what a voltmeter can do is it can measure particularly voltage drops across resistance pieces, while also not inhibiting the ammeter reading of the entire circuit as a whole, meaning that both pieces of equipment can accurately track data. The third part of the experiment was determining the voltage drop around the circuit. Quite simply, the circuit from A to B crossed the battery, or the two batteries. From B to C, it crossed an ammeter. From C to D, it crossed the first resistance piece. D to E, no resistance. E to F, another resistance piece. And then G to H was the ammeter before completing the loop again. The overall result is that the summation of the voltage was zero, which just proves Kirchhoff's loop rule. Part four was calculating the resistance for each piece. So the resistance from the first and second resistor, which was the 47 ohm and 100 ohm resistors, were calculated to be 47.25 and 94.79 ohms respectively. Any error is mostly due to equipment decay and the presence of resistance in the form of the wire itself, which will be further discussed later. The fifth part of the experiment transferred to an RC circuit. Particularly, this focus was the capacitor, charging and discharging it, and a 10 ohm bulb. Some basic analysis of what we got experimentally took about 10 seconds for the 10 ohm bulb to both charge and discharge. Um, Probably the errors were mostly on our part for timing, or possibly the decay in the wiring or the bulb, uh, leading to inefficiencies in either charging or discharging, making it happen faster. The last part of the experiment was simply changing the bulb out in the RC circuit to one of higher resistance. By changing it to higher resistance, we doubled our time, um, which mostly makes sense. Of course, it's an exponential relationship of voltage drop to resistance. So this is not entirely accurate, but once again, any error was most likely due to the equipment itself having some form of decay or timing on our part. The final question was simply, would a capacitor instantaneously charge without the presence of resistance in a complete circuit? Ideally, yes, but in reality, no, because even the most conductive materials have some inherent internal resistance, which would then make it so the capacitor would not instantaneously charge.